You want to grab that?
There you go. I was just waiting for you to start there.
Okay. Oh, okay. Okay. Fair enough. Okay, good. Just want to make sure that we've got that that recording going. Okay, so Inspire is this easy-to-use tool that can cover all of these different aspects of analysis and optimization. And we're, over the course of these 4 hours, say 3.5-ish with exercises and that sort of stuff, going to kind of scratch the surface of Inspire. We're going to get you to the point where you can be comfortable in the usage of Inspire. Excuse me, just dealing with some allergies here. And get you to the point where you can kind of take this basic knowledge and then continue on your own. So by the end of tomorrow, I'd like everyone to be comfortable with the usage of Inspire, and then can take it on their own from there. Any questions, of course, you can go to our Altair University forums, ask questions, and there's going to be people there that can assist you. So I've got a couple of slides here. Now, I teach my classes, and I teach dozens and dozens and dozens of classes a year. And over the many, many years of teaching classes, I've gotten to the point where I'm not a real big fan of the PowerPoint presentation. The standard training class has an instructor bring up a PowerPoint, and they just drone on about the PowerPoint and read to you a bunch of nonsense on a slide. I'm not a real big fan of that. So I promise you, I'm going to absolutely limit my use of PowerPoints in this presentation. But I do, excuse me, find that they have a use here in just kind of introducing what Inspire is all about. So I'm going to use this as an introduction, and then I'm going to move to pure demonstration. If you've got the student edition, and hopefully you have downloaded the student edition in the time before this webinar, I do know some of you, a number of you have downloaded the material. Please feel free to work along with me. The files that I'm going to be using in this presentation are the exact same files that you have. So Inspire introduction. For those of you who are not familiar with Inspire, and this is a prime example of why I'm not a big fan of PowerPoint slides. A lot of people just kind of sit and read this to you. I'm not going to do that. I primarily like this picture here. Inspire is an easy-to-use tool that enables you as a designer, you as an engineer, you as even a CAD operator to do things that, say, 5 years ago, were limited to the cast of people who were knowledgeable in finite element analysis, who had studied it, who had taken courses on it, who understood finite element method. And analysis was limited to them. Now, we're not looking to take away that capability. We're not looking to replace the analyst, but we're looking to take and put a design tool in the hands of people who perhaps need it the most, and it's those people at the front end of the analysis spectrum, the designers, the engineers, and in the case of this, students. We have found that Inspire is an ideal tool in an educational system because it does not require you to spend weeks and weeks and perhaps months learning finite element analysis, learning finite element analysis tools. It provides you the same level of capability and the same accuracy without having that background. So Inspire takes and designs parts like this, or helps you understand the way a part should look. The typical design process is to take an initial design. Now, this could be, as in this case, a part that is currently being manufactured or has been prototyped, or we could have initial design that's strictly digital, that is strictly has been designed by somebody and is not yet to the manufacturing stage. But we're going to take that, and perhaps we're going to run a baseline analysis on it to understand how our part behaves right now. But then what we're going to do is we're going to take that and convert it into what we call a design space, and we'll be talking about that, and allow Inspire to help us understand what our part should look like, help us realize where material is necessary, and perhaps more importantly, where material is not necessary. Gone are the days where we optimize parts by running a quick analysis on it, and anywhere that is blue and there's no stress in that area, we just punch a hole through there. Those days are behind us now, and now we have a tool at our disposal that can allow us to understand the design structure of our part, understand, excuse me, what our part should look like before that part even exists, and take these ideas, take this knowledge, and convert that into an actual engineered design part that, in this case, is 55% lighter than the original design part. I call this a design of necessity, and this is an intelligent design. And that's what Inspire is all about, helping you develop intelligent designs. A few more examples, and then I'm going to get off of the PowerPoints. I like the examples because it helps people, at least at the beginning stages here of Inspire, understand the capabilities of Inspire and what Inspire can do for them. So here's another example. This is a door hinge for Eurocopter. This door hinge using the conventional design process weighed about 9.15 kilograms and took 3 months to design. So this is a very critical airplane part. And was under some significant loads, both in clamping when the door is closed and holding the door when the door is open. And to be able to go through, design it, analyze it, redesign it, come up with a lighter feature, and of course in aerospace, everything is about saving weight. It took 3 months. Using Inspire, an optimization-driven design process, as opposed to a conventional design process, not only were we able to reduce the weight, bring it from 9.15 kg down to 7.5, but as you can see here, the design time moved from 3 months to 3 weeks. That's what Inspire can do for you. When you're designing things intelligently, you can get better designs that are as strong, if not stronger, more often than not lighter, and can happen in a much, much quicker time frame. Couple more here. Another example of a bracket. This was an automotive bracket. And the reason I like to show this one is not because it has weight savings. We already know that these optimized parts are going to have weight savings, and in this case, about a quarter. But in this particular instance, we were forced to use what we call a casting constraint, a manufacturing constraint. One of the other powers of Inspire is not only can it design parts that are lighter and perhaps stronger, or at least as strong, but it can design parts that we can manufacture as well, and that's absolutely critical. Finally here, a nifty little part, and just to show you how far Inspire and this technology has come, this is an antenna bracket on a satellite that is actually currently in orbit. The original design looks something like this. This was the Inspire developed design, a 42% weight reduction, which is critical in an aerospace situation. But in this case, all the design criteria is satisfied, and that's the last thing that I need to emphasize about Inspire. And the last part that I want to have a slide up for is not only can we design parts that are lighter, that are stronger, or as strong, but they're reliable. And in the case of a satellite, if that part breaks, your multi-million-dollar satellite is now turned into an orbiting pile of garbage. You can't exactly send a repair ship up to fix it. So we need parts that are lighter, that are as strong or stronger, and are reliable, and that's what Inspire is going to give to you. So I know that sounds a lot like a sales pitch. If you weren't interested in Inspire, you wouldn't be here to begin with. So I'm not trying to sell Inspire to you. I'm just trying to let you know what Inspire is capable of, kind of get you excited about this software, and get you to the point where you can use it for yourself. So that's what we're going to do. I'm going to tuck those slides away, I may pop them up just to take a quick check of everything that we've covered, but we're not going to do any slides anymore. From here on out, it's all demonstration. And again, I would encourage you to work along with me if you've got the software. Otherwise, just kind of sit back and enjoy the show. So this is Inspire. Perhaps when you ran Inspire, it looks something like this. This is the big graphics area here. You'll see our model here shortly when I open one up. Along the top here, we have our icon ribbons. With Microsoft kind of kicking off the ribbon craze, everyone is, has fallen in line with that, where you have icons, but those icons can be changed depending upon the feature that you want to be in. And you see up here, we have geometry, we have structure, motion, manufacture, and then I have this Eric's favorite. We'll get to that in a little bit. But the ribbon-based icon system changes the row of icons depending upon the function that you want to be in. It allows us to create big, very easy to understand multi-function icons. Additionally, the pull downs here for File, Edit, and View. First thing I want to do here is come to these two, Model Browser and Property Editor. You can also access them by clicking F2 and F3. These two, I feel, are kind of vital to the functionality of Inspire. They put these little menus here. You'll see what they do as soon as I open up a file, so we may as well open up a file. In the pull down, we of course have our new file, open file, import, all that sort of stuff. But I kind of like the icons. The icons make getting from function to function easier, and I think this files icon kind of highlights one of the unique features about Inspire, and that's the multi-function icon. The traditional icon is about as big as this little eyeball here, and for the most part doesn't make a tremendous amount of sense. The icons in Inspire are large, they're colorful, they absolutely demonstrate the functionality that we're looking to get, and they're multifunction. So this one icon here allows me to create a new session, a blank session, by clicking that little paper with the little star up in the corner. Or I can open a model, or I can save a model. Now, save a model is not active because I don't have any model loaded. But you'll see, depending upon where I click on an icon, determines the functionality that I do. And you'll see that all through Inspire. If I click here, I'm in push-pull linear. If I'm here, I'm push-pull revolve. Here, I'm in fillets. Here, I'm in chamfers. These multi-function icons allow us to put a number of different functionalities into one single icon that go together. So let me come here, and I'm going to click the little open folder. Come to my desktop, Inspire, models, and let me open up this exercise one. Now, as soon as I do that, not only does the file open up here, the model open up, the model browser populates, and the model browser shows me everything that I have in my model. And in this first section, what we're going to do is kind of take a tour around the window of Inspire and allow you to become familiar with all of the functions that are in Inspire. So the model browser shows me all of the different tools that I have here, or all the different features that I have in my model. Each one of these individual solids is shown here, and I can turn them on or off. All of my different forces and constraints are shown here, and they have visualization modes as well as my shape controls. And we'll get into creating forces and constraints and shape controls and all that cool stuff in a little bit. But everything that we have in the model is shown in the model browser. And when I have one of those entities selected, say the design space, down in the property area, I get to see all of the different aspects of that, or all of the different properties of that. So I can see what its name is, and I can change that. I can see the material that it's made out of, the fact that it's design space, it auto calculates the mass, it's visible, and you can see I can turn it off. I can change its color. So all of the different properties of that. If I come to a force, you'll see the force has the value in it, whether it's flexible, if it's distributed, it rotates with the part. So all of the properties for any entity in my model can be accessed and edited from the model browser. Down here along the bottom, we've got some icons. The first of which is this little eyeball. This is our show hide icon. So we saw that we could turn off solids or features in our model using the model browser. If I don't want to have to hunt through it, I've only got 4 solids in my model here. Or perhaps I have a model with dozens of different features. Finding them in the model browser may be a little bit difficult, so I can come here to my little eyeball. I select that. You'll notice that my pointer now here has a little black star attached to it. That indicates that anything that I click on, say that solid, now goes hidden. And when we're in the hide show mode, it shows up as a wireframe. But as soon as I right click to select to get out of it, those features go hidden. If I re-enter it, and if I hold my shift key down, you'll see that that little sun modifier has changed to a white star, and anything that I select now turns back on. Lots of questions.
I'm starting to get to a couple of them.
Code.
Yeah.
Oh yeah. Okay. Okay. Yeah. Just a question here. Main limitations of Inspire over OptiStruct. Inspire actually, I want to address that because it actually uses Inspire uses OptiStruct for its analysis. The big difference is Inspire does topological optimization. I'm sorry. Yeah. Topological optimization. It is linear. Yes, linear only. Change element type in Inspire. You can choose from any element type you want as long as it's a tetrahedron. And was only modeled in Inspire and not OptiStruct. Were they happy with the results with only Inspire? Oh yeah, that's why they put it in space. I guarantee you they would not have put it in space if they weren't happy with the results. So.
And just to add to the element type, for the plate model, so I know because you're showing mostly solids. Yeah. Plates you can choose triads or quads for your element type.
Yeah. Yeah, and keep in mind, Inspire is an insanely easy to use tool, but it does incorporate kind of the best features of all of our softwares, the meshing capabilities of SimLab, the analysis setup capabilities of HyperMesh, and the optimization capabilities of OptiStruct. Inspire is not meant to replace OptiStruct. So, you know, I'm seeing a lot of questions of what can this do, what can that do? Were they happy with it as opposed to using OptiStruct? The idea is for Inspire not to replace OptiStruct, but to allow somebody to use optimization that doesn't want to have to devote the time that necessary to learn advanced pre-processing and optimization parameters. It automates a lot of that. Of course, that means that it has some limitations, but please don't view these as competing products. They are complementary products that as long as your analysis and optimization fall within the parameters of Inspire, it is a phenomenal and very easy to use tool. So we are not looking to replace it. Okay, a couple of other things down here on the bottom, the little camera. That allows us to save a view. So any view that we have, we can save it and then go back to it, which of course then leads to the question of how do we rotate, zoom, and pan in Inspire. Rotation is accomplished through mouse clicks. If I hold the right mouse button down, we get what we call a turntable rotation. If I move my mouse with the right mouse button held down, left and right, my part rotates about the z-axis. If I move it up and down, it just points the z-axis in a direction, and then left and right rotates around it. That's why we call it turntable rotation, because it will always rotate about the z-axis. If I hold my center mouse button down, or my clickable scroll wheel, I get a kind of a space ball rotation around that little X, which is the center. If I want to change the center, I just hold my C key down, left click, and that becomes the new center of rotation. This next icon is the changing between perspective and non-perspective. And then we've got rotate to the nearest principal axis, fit selected, and then add section cuts. We'll deal with section cuts later. If I want to zoom, I can zoom in and out using my middle scroll wheel. And it uses the pointer as the focus of the zoom. And then if I want to pan, I can either hold the left and the right mouse button together and it will pan, or I can hold the shift key down and the right mouse button and it will pan. Okay, so that's that right there. You're gonna get this oriented the way I want. The next thing that Inspire looks to make as easy as possible is the concept of units. And if any of you have done analysis or optimization in a traditional sense using, say, HyperMesh or OptiStruct, units can be challenging. We have to rely on unit consistency. You need to make sure that the numbers that you're putting in are in the unit scheme that you want and all that sort of stuff. And if you want to change from one unit scheme to another, it requires you going in and editing every single material, every single force, the size of the part, all of that. Units in Inspire are seamless. You can see right now I'm in an IPS, inch pound second standard. If I click down here, I get a list of all of the different popular unit schemes. And if I change to, say, millimeter Newton second, now everything has changed. My part has changed its size, well, has changed its values of its dimensions to meet that. It has not changed in size. If I come here and let me click this measure box, if I put a measure box around that part, it shows me the overall dimensions of that part. And as I change, you see those dimensions change to reflect that exact same size in whatever unit scheme I'm in. Also, if I come here, let me grab that force. You see the magnitude of the force is 14,500 newtons. If I switch to inch pound second, that automatically adjusts to 3259.72 pounds force. So units are seamless within Inspire. You can change them at any point in time, and it will have zero effect on your analysis other than to guarantee that whatever your results are, they're in the unit scheme that you want them to be in. So let us see what Inspire can do for us. Before we kind of get into the nuts and bolts of Inspire and go through a lot of these functions up here, let's see what Inspire can do and what it's designed to do. This part has been set up. By the end of this class, hopefully we'll understand all of these different features and aspects of this analysis. So I'm just going to come here to structure, and I'm going to run my optimization. And if I click run here, we'll talk about all of this stuff later. If I click run here, it will run the optimization. Now, I'm not going to tie my system down doing it. It takes about 3 to 5 minutes to do that. So I've actually already completed that. As soon as that optimization is done, I click that little flag right there, and I see my part. This is what Inspire, this is what in the background OptiStruct is telling me that my part should look like if I want to get rid of 70% of the material, but make sure that the remaining 30% of the material is as stiff as possible. And it maybe was a little bit overzealous, so let me beef it up a little bit. And you see, that is what Inspire can do for us. It can take and create a design that otherwise we would not be able or capable of designing on our own. Nobody could visualize this pattern of ribs, but this is the ideal pattern of ribs necessary to make this part as stiff as possible, while at the same time removing 70% of the material. And in addition to that, once I'm done, I can click this Analyze button, and now it will go and actually run a linear static analysis of this part. So I'll let that process in the background. And we'll take a second here and just ask if there are any other questions from the audience.
Right now, there's none
about
on the board, but they can, if you want to, they can pose a question.
Yeah, so I'll take like 2 minutes here just to allow this to finish. And this file, as well as all of the other ones that I'm going to be using in these demonstrations and you'll be using in the exercises, are available via download. If you look in the chat window, Darius has put the link to download the, to download the files, to download this entire class, including the PowerPoint presentation for this class. Okay, since there are no questions, we'll just come straight here. I'll click this little flag up here at the top of the analysis, and now we can see
Eric,
the results of.
Do want to add that I ran that model on my computer, and it was barely 2 minutes. It was probably just a tad under to do the optimization.
Okay. Yeah. It's, in fact, if I come back here, I'm sure it's done. Or I never clicked go. It's just I didn't want to, have it sit and go while we're going. But the analysis and optimization is usually relatively quick, especially on simple parts like this. They can take time. There is no doubt. It is a high-level optimization, so it can take time. But the results that we get and the understanding that we get from our part will allow us, will essentially make that time very worthwhile. So looking at our part right here, this, and we come to factor of safety, looks like we're pretty good on the factor of safety. Let me adjust this. So you can see I pretty much have nothing in my part that is a factor of safety of less than 2. Effectively, what that means is it looked at the material yield strength of my material that I assigned to my parts in there, and I am at least 2 times the yield strength of my part. So this works. This design works. I could now put it to use. Now, this isn't a push button, get part type scenario. Our goal isn't to take the engineering out of your hands and replace it with a machine. Our goal is to give you a tool that can give you the information necessary to create an intelligent part. So what we're going to do with this is then get this out of Inspire, typically in a geometry file, bring it into a CAD system, and then within the CAD system, design a part, which kind of comes back to this right here. This is what Inspire created, but this was the ultimate design. Take the ideas from this and use those to design an intelligent part. Okay. So let's just make sure we covered everything that we needed to in that section. Yeah, we talked about the multifunction icons, talked about the ribbon structure. Let's move straight into model setup. So we're going to go through and we're going to talk about the creation of loads, constraints, moments, all of that sort of fun stuff. And then we'll set you up in an exercise at the end of this and allow you to use Inspire for yourself. So I'm going to come here and I'm going to say File, Open. And I'm going to say Don't Save. I don't want to bother saving that. And I'm going to come to this Exercise 2 part right here. Now you notice this Exercise 2 part is no longer a solid thinking Inspire model. It is a parasolid. I believe that's what X_B is. And I click Open and I click Open. All geometry is considered an Inspire file type. We can open up any geometry, whether it is, come back to here, whether it is a parasolid, as we saw with an X_B, CATIA V4, CATIA V5, IGES, Inventor, JT, SolidWorks, STEP, UG, all of these different files we can open up in Inspire. And we just open them up as geometry. And the geometry comes in. Now, if I want to run an analysis on this, I need to prepare this. I need to, first of all, define the type of material that it's made out of. I need to define constraints. I need to define loads, perhaps masses. I can even define temperatures. So let's go through kind of the structure aspect of this. So the first thing I want to do is make sure that this part is made out of an appropriate material. And if I come here and accidentally turned it off, if I come to the part, I come down here to material, say it says material, Eric's material. Well, that's not an appropriate material. Why did it do that? Well, I have created numerous custom materials. Not numerous, apparently I cleared it out. I've got one custom material in there. And I created in a previous demonstration. And if I come here to my file, preferences, and come to materials, you see that the default material is that one that I made. I can set the default material to any of my custom or any of the standard materials that are incorporated into Inspire. And everything from AISI 304 all the way down here to plastic nylon are material properties that have been included in Inspire. And whatever I select in the default will be automatically assigned to any part that is brought in. But just because that's the default doesn't mean I have to keep it. I can right click on this, select material, and grab from the list. Or if I come to my little materials buttons here, I can come to my materials and add as many materials as I want. For those materials, I need to enter in the Young's modulus, the Poisson's ratio, the density, and the yield stress of that material, as well as the coefficient of thermal expansion if I'm looking to do a thermal analysis. And I just simply come to these and enter in what I want. Because I'm in a meter Newton second, my stresses or my pressures are going to be entered in pascals. If I were to switch this to millimeter Newton second, it becomes megapascals, or IPS, it becomes pounds force per inch squared. But the neat thing is, say I'm working in inch pounds, but I know my yield stress is 206 megapascal. Well, I can type in 206 MPa, and as long as I use the appropriate abbreviation, it'll automatically convert that to whatever unit scheme I'm in. And you see if I come back here to there, 206 MPa. So we do truly try to make units as seamless as possible. So now if I come here to material, I could select material 1, or I could grab any of the materials I want from there. Now that I've defined a material, you see it automatically calculates the mass of that part based upon the material and the volume of the part as a result of the solid. And from there, now I need to begin to define the parameters to run an analysis on this. And in particular, I'm looking to create constraints or supports, as we call them, loads, pressures, moments, whatever necessary to simulate this analysis. So I'm going to start out with my constraints, or what we call supports. This icon right here, again, a multifunction icon. If I select down there, I apply supports. If I select up here, I apply a force. If I select here, I apply a pressure. Here is a torque. So if I select that, you see that my pointer now has this little modifier on it. Looks like a little triangle. That's the symbol for support, and that means that anything I click on the geometry, I put a support on. And as I move across my geometry, you see up here at the corner, it puts a little dot at the top of that triangle. If I come here, it puts a line. If I come here, it puts a surface. So I can indicate any of the geometric features that I want to put that support on. Or I can even come here, and if it detects that I'm selecting a cylinder, it will allow me to create a cylindrical support. We'll hold off on that for a minute. Let me come to here, and I'll just grab that point right there. So it now has created that point, the constraint on the point, and has put this little triangle on there, indicating that that point is now held in place. Well, maybe I don't want it held in place. Maybe I want it to be able to move in a certain direction. Well, if I double click on that constraint, it opens up these little arrows here. And if I select an arrow, that arrow turns green. And now if I right click to get out of it, you see that I get these little roller wheels on my constraint. And those roller wheels perfectly line up with that axis that I freed up, showing me that that point is now free to move linearly along that axis. If I then say free up this axis too, you'll see my constraint now has this caster ball on it, showing that it's free to move in plane, but not out of it. So if you're familiar with finite element analysis, you'd know this as degrees of freedom. So we can alter the degrees of freedom on this by simply clicking it and graphically selecting to free up a specific direction. That works whether I put a constraint on a point, a line, or a surface. So say I click that surface right there. Now this is one of the big advantages Inspire has. You'll notice that that constraint has been created normal to that surface. To do that traditionally, I would have to create a local coordinate system, assign it to the nodes on there, and then assign the axis to those nodes so that the constraint would take that orientation. But with here, it automatically did it. And if I come to this, and I come to this little icon right here, move, I can orient that in any direction that I want. And I can always come back to here, click normal, and have it automatically go normal to that surface. So creating constraints is very easy. And I have the ability to create a constraint on a cylinder. So if I select that cylinder, it creates a slightly different icon. The cylindrical constraint puts a constraint at the center of a cylinder and then locks it in place. But if I now select that, now I can click that arrow, which says I'm now free to move along the axis, or free to rotate about the axis. So now it's as if I put a pin through there, but I can't move perpendicular to the axis. So constraints on points, lines, and surfaces allow me to alter and rotating around the axis. Now let's take a look at forces. Forces are this icon right here. If I select that, again, I can put a force on a plane, on a line, on a point. If I select that point, it gives me a force. I can align it with any of the cardinal axes, and I can reverse it. Or I can select my little move, and if I know I want it 35 degrees off of normal, I can just come here and rotate it to 35 degrees off of normal. Or maybe it's not 35, it's 37.354. Well, I can come in here and type negative 37.354, and now I'm exactly there. And that works whether I'm putting a force on a point, a plane, or a line. And the nifty thing about doing it on a line or a plane is I don't have to worry about distributing it. It will distribute it for me. If I say I want 100 pounds force perpendicular to that, it will automatically distribute that 100 pounds force across this entire surface. And I can do along a cylinder. You see it puts it at the center of the cylinder, and then I can orient it however I want it. And I can always see what surface, point, or line a force or a constraint is assigned to by just simply clicking it, and whatever turns red is what that applies to. Pressures work the same way. I can put a pressure. And it will distribute a pressure. Now, one of the things here that I can do with a force on a cylinder like this is I can change this to either a bearing force or a traction force. The bearing force is really cool. If I change it to a bearing force, you see it takes and puts that force like a bearing load on there. So it's following a cosine function of diminishing that load as it gets around to 90 degrees. Or if I change it to a traction force, you see it puts a force, so as if I put like a rubber pin in there and I'm turning that. It puts a traction force along the edge. So we can create some pretty cool forces in there. And force displacement. So let me get rid of this force here. Let's say that I want to put a force on the center of this not as an actual force, but I know that in a worst case situation, this is going to move 0.01 inches in the z-axis. Negative. I'll make it 0.1 so we can see it a little more. There we go. So now what will happen is, as opposed to putting a force on the center of that, it will take that node and move it 0.01 in the z-axis, and the resultant stress will be as a result of the displacement of that. So I don't need to know what the exact force is. So I can use an enforced displacement as a force as well. I can do G loading or angular velocity and acceleration. I can define overall gravity for my part, the direction, and the acceleration. The big blue arrow shows the direction, and the value here shows the acceleration. I can apply a temperature to my part. So it's a delta T in this case. Or I can assign what we call a non-structural mass or concentrated mass. So again, let me get rid of my enforced displacement here. Now, as opposed to a force or an enforced displacement, I know that I have a 500-pound mass hanging off this at a certain CG. Well, I can come here to my concentrated mass. I'll put it there. And now come and move it. And then all I have to do is say, apply it to here. And now that mass has been applied to that, attached to that surface. And in fact, I can come here and I can put in the actual XYZ coordinates of the CG as opposed to just moving it. So it's as if I've hung a mass off of my part, and now that will act as the force in my part. Of course, I need to make sure that I have my gravity properly assigned. And when I'm all set, I just simply come to my analyze here. I tell it what sort of analysis I want to run. I can do a normal modes analysis and request a certain number of modal frequencies. I can do a buckling analysis, or if I leave those off, I'm just running a standard linear static analysis. The option for speed or accuracy. Faster does first order tests, more accurate does second order tests. And then contacts, we'll get into those, so we'll just leave that. If I want to incorporate gravity, so if you're doing a concentrated mass, you had better make sure that you incorporate gravity, and then what load cases we want here. And I just have one of them. Now, the nifty thing about load cases is I can create as many load cases as I want. All I have to do, so say I've got my concentrated mass here. I also want to put a force over here on that side, and we'll put a force here on the top side. But I don't want those all acting at once. I can come to this icon, open up my load cases. I'll add a second load case. We'll come to the first one, and maybe I don't want those forces. I just want force 6 on that load case. But on this load case, I want forces 1, 2, and 3, and then I want my supports on there. So I can pick and choose from these. And then when I run my analysis, I can let it know which load cases I want to run. They'll all run in the same analysis, but they will run independently so they don't like add on top of each other. And that's how we can set up an analysis. and then all I have to do is run it. I also have the capability of doing inertial relief analysis. If you're familiar at all with inertial relief, it's an unconstrained analysis used for spaceships and airplanes, where you don't necessarily have something holding it in place. It's also used in structural parts where your loading and your constraining occurs at the exact same point or points. Okay, so at this point in time, let me see here. I'm going to open it up for any questions that anybody has. And if we don't have questions, we'll have you work on a quick exercise. Okay, since it doesn't appear we have any questions, if you open up your manual here and you come to page 53, exercise model setup, this is going to have you run through and put some constraints and forces on this part, set up a couple or two different load cases and run the analysis on them. We'll give you about 10 minutes or so to work on that. You may get it done in that time, you may not, but just to kind of keep things going, we'll limit the exercise to 10, maybe 15 minutes, because we're doing pretty good on time. The analysis, we'll talk about that, and then probably connections, and we'll wrap that up for the day. So 10, 15 minutes tops to work on the.
Okay. Or there is a question in the question tab if you want to.
Here we go. Oh, sure. What are they at the bottom here? Yep. Does a distributive force have to be applied to an entire face on a part? Yeah, so any surface you get applied to, if you don't want it applied to an entire surface, then you have to have that surface split. But any surface that you click on, it will apply to the entire surface.
So a workaround would be if they, split the surface, then they can get it to a smaller part.
Yep. And as you're going to find out when we get into the connections portion, everything is automatically connected, is bonded together, any surfaces that touch. Okay, so give you 10 minutes or so, 10, 15 minutes to work on this exercise, and then we'll move on to results and connections, and that should wrap us up for today.
Got it.
There we go. Okay. Okay, so when everything is complete, you get this lovely little green flag above your analysis here. And all we need to do is click that, and we get to our result window here. So the result window is going to give us a number of different pieces of information. And the idea here is what we're going to do is we're going to take this part. We're going to kind of walk this part through the entire design process. And as I said before, this is a hinge for an airline door. So let us imagine it looks something like this. That's better. So the door frame is going to be right here. This is going to be sticking out, and the door is going to be hanging off of this little guy right there. And we're going to have, it's actually probably upside down. Yeah, it's going to go this way because the force is pointing down. So in one particular load case, we're going to have a vertical load case, which is this right here. And that's going to be the weight of the door hanging from there. But in another load case, the lateral, let's turn that on right there, you'll see there is now a force in this direction. So this now is going to be the force of, there it is, in that direction right there, of this hinge holding onto the door, pulling it in and keeping it closed. So we've run two different analyses. When we run the analysis and we get to the result page, it automatically brings us into factor of safety. And factor of safety is based upon the yield strength of the material. And I'm going to bring up these PowerPoint slides again, not to bore you. That with these slides, you will see all of the different types of results that we can view in Inspire. And so I find them to be a good resource for you guys at a later date, but we don't need to go through them all. Let me just do this, and hopefully, there we go. So you'll see displacement, factor of safety, percent of yield. So it goes through and explains all of these different features here. So displacement, I can view the displacement, factor of safety, percent of yield, pretty straightforward. Tension or compression, this is just von Mises stress, but showing the sign, showing whether it's in tension or compression. Shear stress, von Mises stress, and the major principal stresses. So I can go and select all of those. You see that's for the vertical case. I can also go to the lateral case and look at those. I can animate this. Now the animation is automatically going to scale up to make sure that you can see what's going on. And I can access that from this little guy right here. If I select that, you see it is auto-scaled by 184.4 times. And it auto-scales just so you can see what the deformation is. If I turn that off, you're not going to be able to see anything. You may see it like kind of jiggle a little bit. But I can turn that off, and I can manually set a scale. If I say 1, you see, that was pretty boring. Even 10, I'm not seeing much of any, just a little bit. But that auto-scaling just allows it to automatically indicate a value that shows me the, allows me to see what the actual deformations are going to be. In any result, I can come to this little slider bar, and I can move it up so I can isolate things at a certain level. So right here, I'm at 4. Anything that's being shown has a less than 4 factor of safety. 100% of yield, I can do this. And I'll come to von Mises stress. If I come to here, you'll see that it shows me the peak. It's contouring pieces versus the peak stress. If I change to aluminum, it doesn't look like it changed a whole lot. But what it does is it changes the contour now so that the failure is above the yield stress of the contour, or the material that it's made out of. So it becomes material dependent. I can also come to, where is it, right here, and select interpolate during animation. And what that does is it interpolates not only the animation, but it interpolates the results as well. So that they, so it looks like they kind of form as I'm going through. I can also add callouts. If I select a point here, it will tell me what the stress is on that point. Oops, didn't select the point I wanted. Let's grab that point right there. There we go. So now it shows me what the stress is on that point right there. I can also get a list of all my callouts, and I can click this and it will automatically put a call out at the minimum and the maximum point. The stresses that you're seeing are being shown in what we call a divergent plot. A divergent plot is a little bit different than perhaps what you're used to seeing. What you're used to seeing is what we call a rainbow plot. A rainbow plot has the lowest value in blue, the highest value in red, and then the whole rainbow of colors in between them. It is the traditional way of showing FE results. It has been decided, or there are studies showing that that actually is a tad distracting because it's showing you too much information. Do I really care if I'm 5 times under yield or 7 times under yield? Probably not. The divergent plot, on the other hand, is a 3-color plot. And aside from being rather patriotic looking, it shows me the 3 things that I'm primarily interested in. And those 3 things are what is below yield, what is at yield, and what is above yield. If it's below yield, it's blue. If it's at yield, it's white. And if it's above yield, it's red. I can change that. If I come to here and select legend colors, and I'll come to my, what am I on, von Mises, I can change this to a, oops, I did it. Von Mises, oh, darn it, keeps changing. There we go, rainbow, click OK. And now I can see the whole rainbow plot. So we're not going to force you to use divergent if you don't want to, but it's an interesting concept that allows you to just focus primarily on the things that you are interested in. If I come to displacement, I can see the displacement. I can change the displacement to a rainbow plot as well. But my only other option then is single color, which is kind of hard-coded to this less than lovely shade of brown, but I guess that's probably most visible or something like that.
Eric, I'm going to
go ahead.
also ask you to show my favorite option. And you know what my favorite option is.
Yes. Darius's favorite option. So in general, we tend to put the mesh in the background. So we don't focus on mesh in Inspire. And the reason for this is kind of manifold. A lot of the people that we deal with Inspire don't understand mesh or don't know the concepts behind mesh. But there are many people who use Inspire, fully trained FE engineers who are using Inspire because it's really easy to use, because it's quick and very accurate. But they oftentimes want to know what the mesh looks like. And once you've run a part and you analyzed it, you get this little extra icon down here. And you'll see it says show elements. If I click that, it shows me what my elements are. And one thing that it does show quite well, and let me stop this animation, is the quality of the mesh that has been generated through SimLab for this analysis. And you can see this is a very high quality mesh. The size was auto-calculated, but when we came to analysis, we can control that element size. And you can actually even control element size on individual parts as well. So while we tend to put mesh in the background and do things automatically, we do allow you the ability to control the mesh as well. And you'll also see once I'm out of the result, I don't have that mesh button, but if I come back to my results, then I can turn my mesh on again. And as Darius mentioned, he is absolutely enamored with the show mesh option there. So.
Yeah, because typically when other tools that try to do something similar, the quality of the mesh is just, you know, they hide it. They don't let you see it, but if you can, it's atrocious.
Yeah, we hide it because we don't want to bother you with it, not because we're trying to mask the fact that we've got bad mesh, because we don't. We have excellent quality mesh. So we're happy to show it to you, but the default is to just kind of keep it in the background because we don't want you to be bothered with the mesh in this. We want you to have the confidence that the meshing tool is going to create a good quality mesh, and we can leave that all to an automatic process in the background. But if you do want to see it it is right there, and that is this icon. Just please remember, and don't get frustrated if you don't see it, the only time you will see this is when you're in the results function. Once I leave the result function, that button goes away. So if you're looking for it, make sure you've run an analysis, and then you can go to the result function, and then you will see it. Okay, so we're doing good with timing here. Got about a half an hour left, which means I got just the right amount of time to do the connections and then have you work on an exercise of connections, which leaves us in a fabulous position for tomorrow, excuse me, to deal with geometry editing and preparing ourselves to run an optimization. So before I shift gears and move into the connections chapter, does anyone have any questions before we move on? So if you do, please feel free to post them into the chat window, and we can address them right now. Otherwise, ask them as they come up, and Darius will be able to type in a response. Or if he needs to send it over to me, he will. But last call for questions before we move on. Okay.
Excellent.
Okay, lacking that, yep, let us move on to the next section here. So I'm going to come here, and I'm going to open up this model right here, exercise 4. Now, exercise 4, this is, we're going to take a bit of a pause. I told you we're going to walk through this hinge bracket through the entire process, but we're going to take a bit of a pause here, because what the hinge bracket doesn't do is show us the connection capacity of Inspire. It's a single solid part. So not much to connect when you're only dealing with one part. So what we do is we take a pause, we bring in this quadcopter model here.
Eric, I do want to add one point. If people are using the student edition, you know, the model that you have initially, I think, was made for 2017.2. Student edition is 2017.1. So you'll get a warning saying, you know, the part was made in a newer version. So just so be aware of that. But that's fine. Just continue.
Okay. Okay, but it does open up.
Correct. It does.
Okay, good. Yeah, so it essentially any new features that we're putting to wouldn't be there, but I don't think there was anything that would affect these models anyway. So don't worry about the warning then. But that hinge doesn't show connections well because there's nothing to connect it to. This model is riddled with connections, and this model is a frame for a quadcopter or a drone, which of course are all the rage these days. You can't go anywhere without seeing these little buggers flying all over the place. But the one nifty thing about these quadcopter or this quadcopter model is it is a whole bunch of different solids. And it is a whole bunch of different solids that need to be connected together. And in fact, if I take a look here, I'm looking at what, about 20, 25 different different solids here. So the thing about solids in Inspire, any solids that touch each other are by default connected to each other. Let me say that again. Any two solids that touch each other in Inspire are by default connected to each other. It will create a connection between them, like a tied surface connection. So I could have taken that aircraft hanger or hinge, cut it in half down the center, and as long as those two solids touched each other, the results would be exactly the same. So, and we do that intentionally, so as geometry comes in, it's valid and it'll run. But that's not always the situation that we want. So we do allow you to alter that. And we can take a look at it initially by making sure we're on the structure page here and coming to contacts. Once I select contacts, it's going to calculate all the contacts. It's going to put the model into a wireframe view and show me all of the contacts. Anything in blue is bonded. think of them as infinitely strongly glued together. Anything in green is contacting. So it's as if I've, my mouse on the table here. You can't see it, but you guys are familiar with mice. I'm moving my mouse around and it's moving my cursor around. My mouse cannot penetrate the table. Probably a pretty good thing. But it can slide nicely across the table. That's what a contacting is. It can't go through it, but it can slide across it. And the no contact would be there's no interaction whatsoever, not really widely used. We want our surfaces or our solids to at least be in contact with each other. So what I see here is this little end piece is connected to the arm is connected to this connector piece. Those connector pieces are bonded on the top and the bottom to my plates. All these tubes are connected together. So this is a rigid model that is all bonded together. But that may not be how I want to analyze this. If I have some force on these little arms that are holding the propellers, there is not going to be a distribution of force across that entire surface. That surface is free to move. It's free to slide. Where it's really connected is actually through these bolts. So this isn't necessarily an accurate representation. It would work, but it's not accurate. And the reason why is because what they've done is they've gone through and they've given me all these little solid parts. I've just isolated this. All these, I clicked on the part and selected I for isolate. All of these little parts represent all of the screws that hold this together. So these screws have been screwed in here. And that's great, but that's really not the way I want it represented. I want it represented with an actual connection. So I'm going to come here and I'm going to select all of these socket head screws and I'm going to delete them. One thing that I want you to look at here, these socket head screws are screwed in here, but I also have this big long one going through the top there. And I'm going to come here and I'm going to right click and I'm going to delete all of those little socket head screws. And and then I've got some more right here and I'll delete those as well. Beautiful. Okay, so now I've gotten rid of the solid representation and I want to replace them with an FE representation. And I'm going to do that through the use of fasteners. If I come here, and I'm in the structure ribbon again, if I come here to fasteners and I select it, you see it's going to identify all of these red holes. What it's looking for are blind and through holes. And if I click fasten all, anywhere there's a through hole, it puts a bolt through. And anywhere there's a blind hole, it puts a screw through. Now, these are just graphical representations. What it will actually do is create a 1D representation of these connections. But the most important thing is if I come back here to context, because I did these fasteners, you'll notice that all of my solid connections have now, except for these, because these weren't connected, they're still bonded together. But anywhere I used a connector, a fastener to connect it, it has freed those surfaces up. So now it's the actual connection that's going to take the force of the connection and not as if I've glued these solids together. This is now a very accurate representation of my part. But one thing it didn't do, remember I had that one bolt that ran through these two holes. It didn't automatically create that. And the reason it didn't automatically create that is because they're too far apart. In the case back here, it actually worked because I have these sleeves that are running from the top. So it was able to see a hole running all the way down through. So it could create that. But on the front, I don't have those sleeves. So what I can do here is I can come back to my fasteners, and if I left click on that hole, it highlights it. And if I left click on that hole, it highlights it. And now if I click this, it will identify those two holes and it will create my nut and bolt there. So I can allow it to automatically identify holes, and then I can force it to create holes or create connections as well. Joints. Joints I can set up as well. Joints are similar to the fasteners, but what they are for are situations where things are revolving around other things. So it's like putting pins in there. That the joints doesn't apply to this model here. And then connectors are just a way of manually creating a connection between multiple faces. If I select any connector, you can see I can change it from a nut and bolt to a screw if I want, or I can go a grounded bolt or a grounded screw. And I'll describe the grounded bolt and grounded screw in just a second. But now my model is accurately connected. And if I were to load this up and set it up for an analysis, it would be a reasonable analysis as opposed to just bonding everything together. So quickly in summary, I go to fasteners. It automatically finds my holes. If I want to, I can come in, let me come here and delete all of those. It automatically finds my holes. I can manually create them by selecting the hole, or I can select fasten all and it will automatically do it. If the hole runs all the way through, if it's a through hole, it creates a nut and a bolt. And if it's a blind hole, it creates a screw. And then if I want to add, I just left click to select the two holes I want to align, and then click the one where I want the bolt to go, and it will automatically create that. And then again, when I do that, it updates any connections that were affected by the connectors to be an appropriate contacting surface. I can manually change them. So say I wanted it bolted, but I also want to glue this all together. I can click on that surface, click bonded, and it will change, or contacting. So I can manually change surfaces as well.
Eric, question. Can you add preload to these bolts?
Preload to the bolts. Yeah, if I come here to the fastener, I can, so if I select a fastener and I come here to the properties, I can enable pretension and I can put pound force onto that bolt.
Perfect. Thank you.
Now here, actually, I'm kind of glad you asked that because let me do this. Let me fit my part. Let's say I wanted to pretension a whole bunch of these. I can manually select them, or if I drag my left mouse button, I can select a window. But you notice that my window is grabbing anything that it touches. So if I drag a left, all it has to do is just nick it and it selects it. Well, if I drag from left to right, it does that. But watch what happens if I drag from right to left. It will only select things that are fully within that box. So I can use it to select individual bolts. So you see, I only got the bolts here because I drag from right to left. So left to right grabs anything the window touches. Right to left grabs only things that are fully within inside the box. Okay, so let me come back here and let me open up my exercise 2 here, because there's one more thing I want to show you in regards to the connectors, and that is the grounded bolt or the grounded screw. So if I come here to fasteners, it's not detecting any through holes. So I'm going to manually grab that and I'll put a bolt through there. Oh, you know what? Let me reset that. Edit, undo, and yeah, it keeps wanting to, darn it. Yeah, it's viewing that whole box. Let me see if I can find a different way of going about doing this. Let's see here, and let's change that. And whatever. It's the graphic is not pretty, but it would create it properly. I don't know why the graphic won't align. So let me just do it actually through here, so it looks prettier. So we'll just put one through here. There we go. Got a big grounded bolt there. So when I put this through a hole that has no mating hole, it automatically sets it as a grounded. Or I can, as you saw, I could change it. Now, what a grounded bolt does, or a grounded screw, is it creates the entity and then locks it in place. And you might say to yourself, well, what's the difference between that and just putting a constraint on that hole? Well, in this case, nothing. They're the same thing. But the reason I mentioned the grounded screw or the grounded bolt is because ultimately when we get into optimization, if I come down here, you'll see that my grounded bolt or my grounded screw has this not only pretension, but has the ability to have optimization enabled. And if I select enable optimization, what that will do is it will automatically calculate the axial and shear force required to break that bolt or screw. And it's based upon the material that it's made out of and the size of it. But I can override that and manually put in an axial force and a shear force. And what will happen is in the optimization, it will also use that as a constraint on the optimization. It will attempt to prevent, through its design, enough force at that hole to cause a failure of your bolt. So now you can incorporate bolt failure into your optimization. If I just put a constraint on it, there would be no way to limit that. So a nifty little feature that a lot of people don't know about. And it looks like another question has popped up here. Might it be that the surface for the screw head was too small? Oh, in regards to the
graphic issue, I think. Yeah.
Yeah, that could it could be. Yeah, I don't know why it did that. I know that when we get to tomorrow when we get into defeaturing and creating non-design space, I know that this becomes an issue again. It really likes this little cutout here for whatever reason. And so I think it's just a graphics issue. It doesn't like it. And yes, it could be because the surface is too small. No clue, but I do know that it did detect the hole and it would create an appropriate feature in there. And again, these are just graphic. It has nothing to do with the creation of the entity itself. The entity will be a one-dimensional entity. And that takes me almost exactly to 520, which is where I wanted to be. If you come to chapter 4, there is a quick little exercise that's going to run you through the quadcopter, let you play around with that. That will take us to where I wanted to be at the end of day 1, which is the completion of all of the analysis portion. And that gives us time to do our chapters tomorrow, which are going to be taking this part here and defeaturing it to the point that we can set it up for an analysis or an optimization, and then running the optimization and reanalyzing the optimized part. So I will say, does anybody have any questions? And if there's not, then please take a look at this quick little exercise. That will end things up for the day, and we'll pick it back up tomorrow at 3:35 Eastern time, 3:30, 3:35-ish, and we will go through geometry and optimization. I appreciate your time today. There were some very good questions. Hopefully you've had an opportunity to run through some of this stuff now, and we'll pick things up tomorrow, and as promised, by the end of tomorrow, you'll be able to run a quick optimization. But I will stick around until 5:30 Eastern time if anyone has any questions while they're working in the exercise. But other than that,